Today, I would like to talk about the treatment of bone fragment when plate fixation is used for forearm diaphysial fracture using finite element analysis. Factors necessary for bone fusion involved biological activity and physical stability. It is believed that the strain at the fracture site should be controlled below 10% to lead to bone fusion in terms of physical stability. However, in clinical practice, there is no way to measure the strain between the bone fragments, so physicians treat the patient based on their experience. Therefore, the purpose of this study was to evaluate the appropriate plate selection and fixation method for fracture by measuring the strain at the fracture site using finite element analysis. Subjects were modeled using CT DICOM data of 5 forearms. First, the fracture type was a simple transverse. The fracture was assumed to be a contact condition and friction coefficient was set to 0. This fracture model was fixed with 6 screws using 7-hole locking plate, and bending model was then created with distal end constriction and 40 Newton load applied backward as a proximal end. Here is a contour map of the equivalent stress in the bone and plate. Using this model as basis, we have examined various models. First, I would like to discuss the width between the bone fragments. 4 different models were created with widths between bone fragments range from 0.1 mm to 2 mm. Soft tissue were placed between the bone fragments to simulate the granulation of the hematoma and initial healing process. First, the minimum principal strain at the fracture site is shown. The narrower the gap, the smaller the minimum principal strain. If the gap is 0.1 mm, bone healing cannot be expected. On the other hand, when the gap width is narrow, the bone fragments are in contact with each other and equivalent stress on the plate is reduced. As the gap width increases, the stress on the plate increases. When the gap width is narrow, stress are directly transmitted through the bone. Narrowing of the gap between bone fragments increases strain at the fracture site. It is little gap that causes serious problem. In simple transverse fracture, it is important to ensure absolute stability, which leaves no gap between the bone fragments. Next, I would like to discuss the difference in contact patterns. First, I have created a model where the cortical bone on the side opposite to where the plate is installed is in contact. Next, I created a model where the cortical bone is in contact on the same side as the side where the plate is installed. And we compare this with the full contact model and the non-contact model. When the bending force is applied to this model, it can be seen that the equivalent stress occurring in the plate is mitigated in the model where the opposite side is in contact. The model with the bone on the opposite side of the plate in contact also has less strain occurring in the plate gap between the bone fragments, which can be expected to aid in the bone healing. On the other hand, if the same side as the plate is in contact and there is a gap on the opposite side, it results in the degree of the strain that causes instability. bones that suppress strain are subject to corresponding load. In the case of fixation method that is only partially in contact, the stress on the bone increases overwhelmingly, especially in models where only the side with the plate is in contact. Very high stress occurs locally. Therefore, it can be said that the contact surface of the bones should be made as wide as possible. The following 2 points have been understood. First, it is better for the bone fragment to have at least some contact. Second, if there is only partial contact, it is preferable on the side opposite to the plate. Of course, it goes without saying that one should attempt full contact to maximize the contact area as much as possible. Finally, we discuss about relationship between the fracture type and strain. We have created model for both a transverse fracture and comminuted fracture, each with a gap width of 1 mm. Similar to before, we have inserted soft tissue equivalent to granulation tissue. The equivalent stress on the plate was greater in comminuted fracture. This is thought to be due to the increased load on the plate in comminuted fracture, as the bone fragment does not come to contact with each other, whereas in transverse fracture, the bone fragment do make contact. On the other hand, it has been found that the strain occurred between the bone fragment is reduced by about half in the comminuted fracture model. From this, it can be expected that if it is a comminuted fracture, it will be possible to avoid the strain that would be load to non-union. This means that even if there are gaps, comminuted fracture do not result in significant strain. In other words, in the plate fixation of comminuted fracture, the presence of the gap between the bone fragment is permissible. This indicates that it is acceptable even with relative stability. In conclusion, it has been understood that when the gap between bone fragments is narrow, the strain on the curves becomes greater, which indicates the need to make contact between the fragment parts at least partially. In the case of comminuted fracture, the strain on the curves is smaller, suggesting that relative fixation may be permission. Thank you for attention.